We will wait for a few minutes. We think we are missing some people. And then we will start. So while we're waiting, if there are any questions about the previous lectures, anything that needs explanation, please feel free to ask. Okay. Okay, so I think we would start. So today, we will look at one of the most useful tools of machine learning algorithms, and that is neural networks. Then associated with neural networks, there's a concept of activation functions. We will see what these are, why do we need that, and finally, we will look at backpropagation through neural network. We'll explain what it is and why it's used. Okay, so most of the slides are, by the way, from Andrew Ng's Coursera's course. So you can find these slides online. I use a combination of these. Some of the slides are mine, but most of them come from deeplearning.ai's website. So let's see. Let's look at a problem. Let's say that you're working at a company, and your company deals in buying and selling houses. You want to buy some houses and sell some houses. Now, of course, the price of the house would depend on a few variables. So let's create some dummy variables, and let's say that the price of house depend on them. So if you're looking at a house, what do you think the price of the house would depend on? I'm looking at the chat. So, okay, so the first thing is location. What else? Okay, size or number of rooms. What else? Okay, type. So I will call it type/age, how old the house is. Okay, and then this would give you some price. Okay, so you have, since you're working in a company which works on this, you have a ton of data. You have a ton of data. You know the sizes of different house, their location, their age, and you know their price. Okay, so I'll call them, let's say, some dummy variable name. So I'll call it location A. So location, I have defined them in like A, B, C, D, E, and F. These are the location types. Size is also a continuous variable, something like maybe 15,000 meters square. I don't know, sorry. That's a huge house, but anyway, let's just do it. And age is maybe 2 years old. And the price for this is, let's say, $10,000. Similarly, you have another house, which is in a location C, size is maybe 10,000 meters square, age is maybe 1 year, and the price is maybe $7,000, and so on. So you have this data, and now your manager asks you like, okay, we don't want to do this thing in ad hoc manner where somebody looks at these variables and then define a price for the house. We want it to be done through a machine learning algorithm. We want a machine a computer to look at these variables and then give us a number for the output. It tells us like whether the price of the house is, let's say, $10,000, $7,000, $8,000, whatever. Okay, what can we do? So that's where neural networks come in handy. That's the type of problem where we use neural networks. So let's do the first thing. Let's use the type of tools that we have seen so far. So what have we seen? We have seen linear regression. Okay, so what if I train a linear regression model for size of the house and price? So if I do it here, I'll get something like this, right? That's how it would look. Do you think it's a good solution? this particular solution, do you think it's good? If you take this to your manager, would he like it? You say, okay, this is the model I have trained. You give it the size of the house and it'll give you a price. Yeah, it's not a great model. And can somebody tell me why? Okay, that's one thing. But let's assume that we want it to be just a function of one variable. So you want to give the price of the house just by based on size. Just comparing that, is it a good model? Well, no, because you can see that after a certain price, after a certain size, the price is negative. So basically, you have to pay people money to buy your house. So this is, well, your manager is not going to be happy about that. He'll be like, okay, that's a short way of taking the business down. So probably what we need is something like this, maybe. And we would see how we can do things like that. Where we have like a function which is piecewise linear and not completely linear. So we would see how to solve this type of problem. So let's look at what basically is a neural network. So the way I'm going to define a neural network, I'm trying to relate it to a logistic regression. Okay. So what did we do in logistic regression yesterday? In logistic regression, we say that we have an output of the logistic regression model, which is sigmoid of W0 plus W1x plus W2x. In fact, let me call them f of x, f of x1, just erase it and write it clearly because we are going to need it. So y hat is equal to sigmoid W0 plus W1 f1 of x plus W2 f2 of x, and so on. Maybe Wm f m of x. And these f1, f2, fm, these are some bases. Okay. The drawback was that you have to specify these. You have to give these bases. For example, we took polynomial bases. In neural network, we want to learn these bases. Okay. So basically, allow me to give you this intuition of the neural network. So for the first layer, okay, these are called layer. So this would be layer 1 of the neural network. Then this would be layer 2 of the neural network, and so on, depending on how deep your neural network is. Okay. So what is a layer? Let's look at a layer. So a layer, these connections, by the way, are just some weights. Okay. So the weight here is W11. The weight here is W12. The weight here is W13. And the weight here is W14. So let me just write the output expression for this. It's called a neuron. Okay. These things are called neurons. So let me write the output expression for this neuron. So I'll use the notation. I'll use Z superscript for the layer. So since this is the first layer, I'll call it Z1. Okay. And then this is the first neuron. So the subscript represent the number of neuron that I'm looking at in a particular layer. Okay. So this part is called Z, and then it's passed through some activation, it's called A. But I'll explain both of these. Let's just first write this Z11. So this would be W11x1 plus W12x2 plus W13x3 plus W14x4. Okay. After we calculate Z, it is passed through a sigmoid function, just like we pass the summation of bases through a sigmoid function in a logistic regression. So the A, which I'm called activation, A11, would be just the sigmoid of this. Sigmoid of Z1. Okay. This is the output of this neuron. Okay. Let's say I have to write the output of this neuron. What would be the output of this neuron? This would be W, let me call superscript 1, just to make sure that we know that this is the weights of first layer, and these are the weights of second layer. This would be 1, 1, W2, 1, 2, and W2, 1, 3. So I'm just going to write the expression for Z21. The linear combination of the second layer's first component. Okay, 2 is for the number of layer, I is for the number of neuron that you are interested in. So this would be W11 for the second layer. And what is the input? The input is the activation of first layer's first component. So this is the input, right? This is the input to the second layer, A11, and then A12 and A13. So this would be W2, 1, 2, A12 plus W2, 1, 3, A13, and so on. Okay. Now, what you can see, what is interesting is that for the first layer, the inputs are the bases, right? The input that the user provides. In the case of house example, it would be the size of the house, the location, and these kind of things. But the input to the second layer is something which is learned by the neural network, right? We don't specify it. The neural network learns it with some combination of our inputs, right? And the input, these inputs are A11, A12, A13. This is something that the neural network is learning rather than us providing explicit basis as we do in the case of logistic regression. Okay, is it clear so far, this point, that for the first layer, yes, you provide the input, but as we go deeper in the layer, the bases, the inputs of these layers are learned. These are not something that you provide. Okay. Are there any questions for anyone? Is everyone clear? Excellent. So let's look at this representation in a bit detail. Let me get an empty slide here. Okay, so let's try to write this neural network representation in some detail. So basically, what did we have? We have 4 input, 3, and then 1. Okay, so I'm going to draw this neural network. We have 3 hidden elements in this, and we have 4 inputs. So x1, x2, x3, and x4. And these are, of course, connected like this. I'm not going to draw all of these, but you can extend it. Right? So let me write the expression for each of these, each neuron of this neural network and the output. So like we said, the Z11, which is this, remember this thing would be Z1 vector, and then this, the first would be the first component of this vector. The second one would be the second component of this vector, and the third one would be the third component of this vector. Okay? Then we pass it through activation, it becomes A. So let me write the expression for Z11. This is W11 x1 plus W12 x2 plus W13 x3 plus W14 x4. Similarly, Z12 would be W21 x1 plus W22 x2 plus W23 x3 plus W24 x4. And Z13 would be W31 x1 plus W32 x2 plus W33 x3 plus W34 x2. Okay, and this is actually a nice set of expression, as in we can write it much more concretely. Can somebody give me a guess as to how I can write it in closed form, in a compact notation? We saw this, by the way, in linear regression as well. So linear regressions, the output were in this form, and then we collected them in a compact form. So yeah, you can write it in matrix form, right? So you can say that Z1 is Z111, Z12, Z13, okay? And then you can have a weight matrix for the first layer, which can be W11, W12, W13, W14, W21, W22, W23, W24, and W31, W32, W33, W34. And the input X can be X1, X2, X3, and X4. And then based on this, you can write Z1 is equal to W1X. Now that's a much nicer notation, right? You don't have to keep track of each individual weight. All the weights are inside this matrix. The output is actually, it's easy to see. This is the weights of the ith layer. This is the output of the ith layer, and so on. Okay. So now, after you have the linear combination of the input to a layer, you pass it through an activation function, in our case, sigmoid. So you pass it through sigmoid, and then you call the output of this A. So A is the sigmoid of Z1. Okay, and sigmoid of Z means sigmoid of each component. Then this A is the input of the second layer, right? So the linear combination of the inputs of the second layer would be W2 times A1, right? And the activation, after the activation, the output of the second layer would be sigmoid of Z2, and so on. You can repeat it, you can write it for as many layers as you want. Okay? Is it clear to everyone? Perfect. So if we look at this, it's again explaining the same concept in slightly easier notation. So if we want to write the flow chart of it for a single layer neural network, first you have the linear part, which is just Wx plus B. Then you have the activation part, which is passing through the sigmoid. Then you have the loss function. If it's a two-layer neural network, the same component is done twice. You calculate the output of the first linear layer, then the non-linearity, then the output of the second linear layer, then the non-linearity, and then of course at the end of this you would have a loss function. So now we have actually technically the tools to write a loss function in terms of a neural network. Remember, if you look at it, this part is like a logistic regression. This is a logistic regression because that's exactly what it is. That's the first layer. And you can see that this is indeed like a logistic regression type of setup. Of course, the loss is not put on top of it. And then this is like another logistic regression. So basically, neural networks is like type of stacking of these logistic regression models to give your learning model more complexity, to allow it to learn something more complex. Okay, does it make sense to everyone? Does B2 comes from the first layer, or is it a hard-coded? No, so I actually did not write biases in my setup, but the biases are present in each layer. So technically this should be plus B1 and this should be plus B2. So they don't come from each layer. They are present as independent weights in each layer. For the ease of notation, I just dropped it, but they are present everywhere. So, and we will see why this is the case. Why do we need biases? Because let me come to the example that we did earlier. So for example, if we come to this example, let me just erase it. No, I cannot erase it because oh, anyway. So let's say that in one model, my house's prices were like this, and I wanted a model to depict it. So we can see that it's a linear model up till this point, and then it's another linear model. So it's a piecewise linear model, and the point of discontinuity is this. Let's call it some x naught. Okay. You might have another data set where, let's say, the point of discontinuity is this. Let's call it x tilde. Okay. How do you tell your model? So these are exactly same models. They're just shifted by some DC offset. How do you tell your model to move along the x-axis? So this is what is controlled by the bias. Okay. So that's why you need this bias term in each layer. The bias basically controls for the lack of a better word, the origin of your process. So if we call this the origin of your process. So where is this discontinuity, or from where should you start the activation process? How much input value would trigger a response at the output of an activation? That's what's controlled by the bias. Okay, is it clear, Lucas? Okay, perfect. Okay, so let's see why do we need this activation function? What is this activation function business? Why do we put it in? Like, why can't we just have a simple stacking of linear layers? Okay, so I'll give you a question. Let's say that I say, okay, I don't agree with this neural network setup. This is wrong, incorrect. What I want to do is something like this. So I want to say that my first layer is just W1 times X. My second layer is W2 times Z1. And my third layer is W3 times Z2. And then I feed this to some loss function. Okay. So basically my output Z3 is W3 times W2 times W1 times X. No non-linearity, no activation function, just a simple composition of linear operations, of linear layers. Okay. And let's say that the size of X was 10. Let's say the size of X was 10 times 1. Let's say W1 was 20 times 10. W2 is 40 times 20, and W3 is 1 times 40. Okay. So what are the total unknowns in my network? The total unknowns in my network is 20 times 10 plus 40 times 20 plus 1 times 40. And this would be 200 plus 800 plus 40. So 1040, right? I have 1040 unknowns in my network, the weights that I'm trying to learn. Okay, it's a good number, a sizable number. I should be able to learn something very nice from this, because it's a relatively large network. But I can write the same output Z3 as Wx, where W is W3 times W2 times W1, and the size of W is 1 times 10. I can do that as well, right? Everyone agrees that I can do that? Just from linear algebra, I can take the product of matrices, and the product of these three matrices would be 1 times 10. As a general rule, if you want to find the size of matrix products, you just write it like this. So the first W3 is 1 times 40, W2 is 40 times 20, and W1 is 20 times 10. And then the inner things would cancel, and the output size would be 1 times 10. Okay. So now doing this thing with 1040 weights is exactly equivalent to this, which has only 10 weights. So whatever you can learn by this 1040 weights, you can also learn by just 10 weights, which is terrible, right? Because you created a big network with so many weights, and whatever you can learn with this network, you can also learn with just 10 weights. So what's the point of going through such the trouble of setting up a large network? So this is basically, you can call it like the collapse of linear layers. So the linear layer collapse into themselves to create just one linear layer. So that's why we need this non-linearity. That's why you have these activation functions in between. Okay, if you have some non-linearity here and here and here, then the layers do not collapse into each other, and the ability of the network to learn something new is intact. Does it make sense to everyone? Why do we need the activations? Okay. Can I see some more yeses in the chat? Or if there are any questions, please ask them. Okay, perfect. It seems like things are clear. So let's look at the one activation function that we have seen so far, that's sigmoid. Uh, um, the property of the sigmoid is that the output is bounded between 0 and 1. If I try to calculate the derivative of sigmoid, um, what would be the values of derivative in this region? What do we know about the derivative of sigmoid function in this region? Small, not 0, but small. Okay, so very small numbers. What can I say about the derivative overall about the sigmoid function? Is there any general global property of the derivative of the sigmoid function? Like, for example, the derivative should be always less than, let's say, 5 or something like that. Can I say something like some global property of the derivative of the sigmoid function? So the sigmoid function is always increasing. I can see it from its graph, right? If it's always increasing, what would be the sign of its derivative? It's always positive, right? So the derivative maybe would look something like this. Because it's quite small here as well. So this is how the derivative looks of the sigmoid function. Okay, something like this. It might not be accurate, but what I'm trying to suggest is that it's very small here, very small here, and some okay numbers in between. Okay, let's look at. So this is basically just an offset version of the sigmoid function. If, for example, you want some negative values from sigmoid as well, you can subtract some 1 by 2 from it, and then it becomes from negative 0.5 to positive 0.5, if you want something like this in your application. We have another activation function, which is this, which is called a ReLU. Okay, I think it's like rectified linear unit. what can we say about the derivative of ReLU function? First, let's write the expression for ReLU function. If I want to write it mathematically, how would I write it? So the function here is x, and the function here is 0, or z, in fact, because I'm calling this z. So the function here is z, and the function here is 0. How would I write it mathematically if I want to write an expression for ReLU function? How would I write it? So x theta 0 minus x. I don't, okay, Heaviside function. Okay, so you are taking a function, multiplying it with Heaviside function. That's fine. That's fine. Okay, that's true. But can I write like a simple expression, something like max of 0 and x? Does it make sense as well or not? So my ReLU function is just the maximum of 0 and x. And when 0 and z, sorry, because I'm writing my independent variable as z. So if z is less than 0, you get 0. If z is greater than 0, you get z. Okay. And what about the derivative of this function? What is the derivative of ReLU? So yes, it's 0 for negative numbers. It's 1 for positive number. What about the derivative at z equal to 0? What is the derivative at z equal to 0? Any guesses? Okay, so the derivative of 0 is undefined. Okay, for a derivative to be defined at a point, the derivative as you approach to that point from left and right should be same. Okay, but if you approach to 0 from left hand side, the derivative is 0. If you approach it from the right hand side, the derivative is 1, which means that the derivative is not defined at 0. Okay, so this is a little bit of a problem, but statistically speaking, you are very less likely to encounter a point exactly z equal to 0 while you're doing your gradient descent or something like that. So things do not break down. Yeah. So what about this? So this is like it's called a leaky ReLU. So rather than having a hard 0 at the for z less than 0, we have a version of z with lesser slope. So let's say the slope here is 1. The slope here is maybe alpha, where alpha is between 0 and 1. Probably 1 not included. So how would we write the expression for this? If I want to write it mathematically, what would this be? Just look at this. This is for ReLU. What would be the expression for leaky ReLU? So it would be max of z and alpha z. I think your expression is probably also true, but a times min of 0 and x, yeah, I think it's also true. It might also be correct. This is probably slightly more. And then the derivative of this is alpha here, not defined at 0 and 1 for x greater than 0. Now, ReLUs actually have had a huge role in the success of deep learning methods, particularly deep neural networks. And the reason for this is what does the, so maybe let's do it on a clean sheet. So let's say you have a deep neural network. So what would a deep neural network imply? A deep neural network would imply that you have multiple layers, right? So you have an input, X, you have a first layer W1, then you have some nonlinearity, then you have W2, okay, then you have some nonlinearity, and so on. Let's say you have M layers, Wm, and some nonlinearity, and then some loss function. Let me call this y hat, of y hat and y. Okay, and let me call the output here Z1, the output here A1, the output here Z2, the output here A2, and Zn, and probably, let's not call it y hat, let's call it Am. So the loss is between Am and y. And let's say I ask you to find the derivative of loss function, or let's call it partial derivative of L with respect to W1. How would you do it? What is the tool in calculus which we use to find derivatives when there is a composition of functions? Any guesses? So we can use chain rule, right? So if you have a composition of function, you can use chain rule, where you take the derivative of each function with respect to its input, and then since it's a composition of functions, you can uh, perform it for any depth of function operations that you have performed. So let's do it. So I will have something like partial derivative of L with respect to Am times partial derivative of Am with respect to Zm plus partial derivative of times partial derivative of Zm partial derivative of Am minus 1, so on, so on, so on. And eventually you would have partial derivative of A1 with respect to Z1 and partial derivative of Z1 with respect to W1. So let me write a few more terms here because I think it would make things a bit clear. So partial derivative of Am minus 1 with respect to partial derivative of Zm minus 1 times partial of Zm minus 1 with respect to partial Am minus 2, partial Am minus 2, partial Z m minus 2, and so on, right? Does everyone understand this chain rule expression that I wrote? So I'm just doing the partial derivative of the output of each layer with respect to the input of that layer. So you see that its loss is dependent on Am. So I take the partial derivative of loss function with respect to Am. Then Am is dependent on Zm. So I take the partial derivative of Am with respect to Zm. Then Zm is dependent on Am minus 1. I take the partial derivative of Zm with respect to Am minus 1. Then Am minus 1 is dependent on Zm minus 1, and so on, right? Everyone agrees with this expression of chain rule? If not, please ask me and we can discuss chain rule a bit, but we have already seen it. So any questions for anyone? If not, just please put a simple yes in the chat so that we can move forward. Okay, so it seems like it's clear to almost everyone, which is really nice. So now I should ask you this. What about these terms? Partial derivative of activation with respect to the input of activation. Well, let's say we had these are sigmoids, right? Let's say that the sigma, the non-linearities that we have are sigmoids. What can we say about these terms, which is the derivative of the output of the sigmoid with respect to derivative of the input of the sigmoid? What can we say about these terms? Remember, we saw this, that the derivatives are zero almost everywhere, and they are non-zero in a very small interval. So what do we expect these values to be? Of course, we expect these values to be quite small as well, because these are in fact the derivative of the sigmoid. Let's say you have m where m is large. Let's say you have 100 layers. Okay, you would have 100 of these terms, right? You would take the derivative of 100 sigmoids with respect to the input of sigmoids, and you see that in chain rule you have a product of all these terms. So if a number is small, and you take it square, it becomes even more smaller, right? Or if two numbers are small, you multiply them, their product would be even more small. When I say small, it means much less than one, between 0 and 1. So what we notice is that, okay, these are small positive numbers, much smaller than 1, and you have a product of m numbers of this. So these would become extremely small. The product of all these terms would become extremely small. And if the product of all these terms is extremely small, it makes the derivative very small. And if the derivative is very small, then we have an issue, because we use algorithms like gradient descent. So if the gradient is very small, then the values are not updated. You cannot learn anything. So that's a problem that's called in literature a problem of vanishing gradients. And that's actually something which hampered the progress of deep algorithms for quite a long time. We couldn't learn very complex things because we could not use deep networks. And we could not use deep networks because we were using sigmoids or activation functions for which the derivatives are close to 0. And when you use a composition of these, the derivative of the loss function would become very small, and you wouldn't be able to learn anything. Does everybody understand the problem of vanishing gradients? Okay, so another way to look at it, like when you use sigmoids, the loss function looks something like this. If let's say I'm plotting loss against a single variable, it looks like this. So although it has a local minima, the slope, the gradient of the function is very small, and if you use a gradient descent algorithm, it would take a very long time to converge to that. Okay, so that's a problem. And in order to solve it, people started using ReLU. ReLUs are actually much better, because ReLUs, the derivative is non-zero for at least, with probability at least half. Because if you take a real number, if you sample a real number randomly, uniformly between negative infinity to positive infinity, half of the time the derivative would be 1. Half of the time the derivative would be 0, right? So that's why ReLUs actually allowed us to do training with deeper networks. If you have leaky ReLU, then it becomes even more better, because the derivatives are literally defined everywhere except for 0, and they are non-zero. So that's ReLU actually. ReLU helped solve the problems of vanishing gradients. Okay, so now it seems like we have a setup for defining our neural network. Let's try to find the outputs of the neural network, and then let's try to train your neural network, because these are the two things which are left. So generally speaking, like we said, we divide it into two parts, a linear part and then an activation part. And it's actually quite simple. You can find the output of each component and write it in a matrix form like this. Okay. We have already derived it, so I'll stick to it. If you want, if I give you an input and some weights, and I ask you to find the output of the neural network, you can do it quite easily, right? So again, this power represents, superscript represent the layer. So the output of the first layer would be X times W1 plus B. Output of the activation would be just input of that activation passed to a sigmoid, and so on. So now let's look at some actual training. How would we train a network? Let's say we have a classification problem. How do we train a neural network? So let me onto the appropriate slides. I can probably do it here. So let's say we have a two-layer neural network. My neural network is given by this. Z1 is equal to W1x plus B1. A1 is sigmoid of Z1. Z2 is W2 times A1 plus B2. And A2 is sigmoid of Z2. And the loss is a function of Y and A2. It's a binary classification problem. Is we said a good function because it gives probability between 0 and 1, but really can give a value larger than 1. Is this relevant? Yes. So generally, if you're using a classification problem, a binary classification problem, the activation function at the output layer has to be between 0 and 1, right? Because we consider output as probabilities. But any other activation inside the network does not have to be between 0 and 1. So you can use relose inside the network, but the output layer has to be a sigmoid if you're doing a binary classification problem, because we want it to be between 0 and 1. There is no constraint on the hidden layers. By the way, anything which is, so we drew our neural network like this, right? So anything which is not an input or an output is called a hidden layer. Okay, so there is no constraint on the hidden layers. They can output any value, any real value, but the output has to be between 0 and 1 because we are interpreting it as probability. Okay, so let's do the entire expression for this. So for the ease of our calculation, I would assume that everything is scalar. Okay, x is scalar, b is scalar, w is scalar, everything is scalar. So my network is basically this. So you have an x, it's multiplied by w1, which is a scalar. It's passed through a sigmoid. It's multiplied with w2. It's passed through a sigmoid, and then there is a loss. And the loss, we already have seen it yesterday. The loss of y and a2 is minus, and we have one sample, log of a2 minus 1 minus y log of 1 minus a2. Okay, so let's take the derivative of loss function with respect to a2. And this becomes minus y divided by a2 minus 1 minus y divided by 1 minus a2 plus 1. Okay, this multiplied by minus 1, so this becomes plus. Hopefully I'm not doing any mistake. So let's do this. This becomes a2 1 minus a2 and minus y plus a2y plus a2 minus a2y. So these two cancels out and this becomes a2 minus y divided by a2 1 minus a2. So we have the derivative of L with respect to a2. I'm trying to find the components of the chain rule. Let's find the derivative of a2 with respect to z1. So write the expressions here again. So z1 is wx1 plus d1. A1 is sigmoid of z1. Z2 is W2A1 plus B2, and A2 is sigmoid. If I'm making any mistake, please correct me because I'm writing them quickly. So, and then there is loss. So the partial derivative of A2 with respect to Z2 would be the derivative of sigmoid, which we did yesterday. And this is, do you want me to recalculate it or can I just copy the value from the previous lecture? Just a simple yes and no in the chat. Should I recalculate the derivative of sigmoid, or should we just use the previous value that we derived yesterday? Okay, so this is, I think, A2 1 minus A2. Okay, so then next we have to find the derivative of Z1 with respect to A1, and this is W2. Next we have to find the derivative of A1 with respect to Z1. This again would be A1, 1 minus A1. And finally, we have to calculate the derivative of, okay, Z1 with respect to W1. This is X1. The derivative of Z1 with respect to V1. This is just 1. So I just looked at this expression and calculate the derivative of each of these with respect to their inputs. Okay. Similarly, here I need one other thing. So this is Z2. Okay, I need the derivative of Z2 with respect to W2, which would be derivative of Z2 with respect to W2 is A1, and derivative of Z2 with respect to V2, which would be 1. So now I have all the derivatives. I can calculate the partial derivative with respect to any variable. So let's try a few test values. Let's take the partial derivative of L with respect to, let's say, W1. This would be partial derivative of loss function with respect to A2, partial derivative of A2 with respect to Z2, partial derivative of Z2 with respect to A1, uh, partial derivative of A1 with respect to Z1, and partial derivative of Z1 with respect to W1. So I'll put in the values of each one of these. So this is A2 minus Y divided by A2 1 minus A2. This is A2 1 minus A2. Z2 with respect to A1 is W2. Then A1 with respect to Z1 is A1. I should have found an open space for this. So let me write them here. Partial derivative of L with respect to W1. So first partial derivative of L with respect to A2. This is A2 minus Y divided by A2 1 minus A2. Then A2 with respect to Z2 is times A2 1 minus A2. Then Z2 with respect to A1 is W2. Then A1 with respect to Z1 is A1 1 minus A1. And finally, Z1 with respect to W1 is X1 or X. So this is the partial derivative of L with respect to W1. Similarly, you can do partial derivative of L with respect to W2. Okay. So this becomes quite easy. One trick which we can do is use the chain rule effectively. It's something like this. So let me keep notation and get a new slide. Okay, so let's draw again the same pipeline. So So we have Z1 here, then A1, then Z2, then A2. So the convention that I'm going to use is I'm going to write partial derivative of L with respect to A1 as dA1. Okay, and I'm going to write partial derivative of L with respect to Z1 as d z1 and so on. Okay, so d would represent partial derivative. So if I take the partial derivative of L with respect to a2, like I said, this is dA2. Okay, if I take partial derivative of L with respect to z2, so partial derivative of L with respect to z2 would be partial derivative of L with respect to a2 times partial derivative of a2 with respect to z2. And we know that this thing is dA1. So this is equal to dA1 times partial derivative of a2 with respect to partial z2. Okay. Similarly, if I need to calculate partial derivative of um, loss function with respect to a1, this is partial derivative of loss function with respect to a2 times partial derivative of a2 with respect to uh, z2 times partial derivative of z2 with respect to a1. And this, we know that this is partial d of z2. So basically, yes, sorry, it's dA2. Okay, and then this is the dz2. So basically, what you need to do is, if you have the partial derivative at this layer, let's say this is dz2, to calculate the partial derivative at a1 or partial derivative of loss function with respect to a1, you just need the partial derivative of this layer, because it's chain rule, right? Everything else stays the constant. So basically, you can iteratively find it. If you start by from the loss function, you can find the partial derivative of a2, then you can use it to find the partial derivative with respect to z2, then you can use that to find the partial derivative with respect to a1, and so on and so on. So that's why it's called a backward pass, because you start from the output and you start calculating the partial derivatives of the variable which are closest to the output, and then go back toward the input. So that's called a backward pass. Okay. Forward pass is starting from the input and going deeper and deeper into the network to find the output. Backward pass is to start from the output and start going deeper toward the input to find the derivative of each layer. Does everyone understand why it's called backward pass? Okay, perfect. So this is again the intuition. They would write all the expression. Again, you can see that dz2 is directly used in finding the derivative with respect to the weights of second layer. And then you can see that dz2 is also used in the calculating the derivative of with respect to the first the way the derivative of the activation function or the input of the activation function of the first layer, and so on. So you can see that they have missed some quantities. So for example, generally you would not see them writing the dA1 or dA2 and so on, because they are not required. All the weights are um, related to z. So z is the output of the function which defines weights. Okay, so you don't need to store them. So that's why they don't store them. They just store dz2, and then based on dz2, you can calculate dw2 and db2. You need to store dz1, and based on dz1, you can calculate dw1 and db1. Okay. Does it make sense to everyone? So implicitly, they have dz1. So this thing is actually dz1, but they haven't explicitly stored it. They just calculate it at runtime. Okay, perfect. So basically, this is the expressions we need. We can add another trick on top of it. So basically, right now, what we are doing is we are saying that, okay, this my my input x is a vector. It goes into the first layer, then the output goes into a sigmoid, then it goes into a second layer, then it goes into a sigmoid, and that's my output. Okay. But nothing is stopping us from doing it for multiple samples, right? So this is, let's say, x0. I can do it for multiple samples. I can say, okay, I can very easily stack my inputs and it would work the same. A2 would now be a big vector. In fact, let me write it a matrix because it's a vector in 2D now. Okay, and you will get the output of for all the inputs in a single iteration rather than doing it for each data point separately. Does everyone understand this vectorization trick? We've already seen it in linear regression and logistic regression, but I just wanted to retouch on it. So does it make sense to everyone, or should I go over it a bit more in detail? Are there any questions for anyone? Okay, okay. So let's, so these are, so you see now these terms become matrices. So this becomes A2 minus Y. The derivative of loss function with respect to W2 becomes DZ2 times A2, A1 transpose. This is NP sum, it's basically a product with a unit vector, but let's write it like this. So these are exact expressions that we would implement in code today. DZ1 is this, and DW1 and DB1 are these. So we will implement these exact expression for a 2-layer neural network. Okay. So again, the entire setup would be something like this. We would have matrix X, which would be the matrix of the inputs, X0, X1, X2, up till Xn. Okay. Z1 would be W times X plus B. Again, when choosing W, the number of columns of W has to be equal to the number of rows of X. And the number of rows of W depends, it's a design choice. It's the number of hidden units that you want. So W would be NH times X dot shape 0, W1. Okay. I'm not going to write the shape of B because it's obvious, but you can do it yourself. Then A1 would be the sigmoid of Z1. Again, the sigmoid of a matrix is element-wise sigmoid. So you just do sigmoid of each element. Then Z2 would be W2 times A1 plus B2. The size of W2 would be an out, with an out is the number of outputs that you want, times NH. Okay, NH is the number of hidden units. And A2 would be sigmoid of Z2. Okay. Now, to calculate the backpropagation equation, to calculate the gradients, what you need is dz2, which is partial derivative of the loss function with respect to z2, and this is a2 minus y. Okay, then partial derivative of w2 is dz2 times this should be a1 transpose. Okay. Similarly, the b1 would be dz2 sum along columns. Okay. Similarly, z1 would be dz2 times w2 transpose element-wise product with a1 1 minus a1. Okay, the W1 would be D Z1 matrix product X transpose, and sorry, D B1 would be D Z1 sum along columns. So basically, you have to implement these expressions in NumPy. Okay, these are just simple implementation of backpropagation equations. Okay, I'm going to put them on the slides on the website straight away so that you can have a look at it and access it while you are writing your code. This is my scribble, which probably is not very neat. So you can use this one. The only thing that you need is this thing, G1 with respect to C1, and this is A1, 1 minus A1. Okay. Other than that, everything is fairly well written on the slides. You can implement it. So I'm going to stop the lecture at this point, and I'm going to allow you guys some time to try to implement it. So let's take some time, like up till 11. We take a break between 11 and 11:30. At 11:30, I will sit with you guys and we will implement not only a two-layer network, but any n-layer network in NumPy by ourselves. Okay, we are going to try all the questions, all the classification problems that we did yesterday. By the way, when you do this problem, just use it for the simple linear regression classification problem that we did yesterday, and try to solve it with this. So you have two variable x1 and x2, and the output is a binary classification problem. So you're going to classify uh, the data with the help of a two-layer neural network. Okay. Is it clear to everyone what you have to do today? Up till 11, that is. Implement a two-layer neural network in NumPy to solve the binary classification problem. Use the data for linear regression questions logistic regression questions that we did yesterday. Is it clear? Okay, I want to see some more yeses in the chat. Thank you. Okay, thank you. So let me stop sharing my screen here. And okay, and everyone, welcome back. Let's resume our discussion. Is everyone back? Could you just put a simple yes in the chat? So that, perfect. So before we start, let's look at the course project. So I've added the instruction for course project under course instructions. So it explains that the course project can be done in a group of 3, maximum 3. You can do it 1 or 2 as well. You would have to submit like a 2-page project report, just explaining what you want to do, the code of the project in a Jupyter notebook, and a 5-minute small recorded presentation explaining what you have done. So I'll give you an example. So let's say you're working, you can use any general data set of the internet. Let's say you look at a data set of the internet, which is, let's say, the same example that we saw, features for house and their price. So you downloaded the data, you created, let's say, a 10-layer neural network, you trained it, and then you tested on the test data set. So that would be a project. I would prefer if you guys use the data from your domain. For example, if somebody is working in geology or petroleum, they might have some processes in their respective field where, let's say, some variables define whether, let's say, there is oil present or not. I'm not an expert, but I'm just giving you some motivation. So then you can use that data and train it on that. just a small project like explaining the data, okay, a small report explaining that data is like this, I use this type of network, and this is the type of results that I get. You can register your project here. This is a Google spreadsheet, so just put the name of your team, the members, your team members, and your project title here. Of course, don't add it in a new cell. Don't um, undo what other people have done, because you guys are sharing this notebook. The entire class will share it. Okay. So, any questions regarding what you have to do for this? Does everybody understands the requirements of the project and what you need to do? Can you choose any topic? Yes, you can choose any topic. Okay. Okay. Any other questions? Okay. So if there are no other topics, let's come back to our exercise, and let's try to set up a two-layer and maybe multi-layer neural network. So again, I have the same data, same type of data that I used for logistic regression. I have a variable X, which is a 2D variable. I have around 200 samples, and I have their label, which is a one-dimensional vector, and I want to uh, train a neural network. So let's first create some architectural properties of our neural network. So what we want two-layer neural network. So the first thing that I have to do, I have to define the number of hidden units in the first hidden layer. How many hidden units do you guys want? Give me any random number, random integer that is, positive. So I'll take maybe 10. Okay. What are the number of input units? What is the size of the input? Could depend on the shape of X. It would be X shape 0, the number of rows in X. And what is the number of output? This should depend on on Y. It should be the shape of Y, the number of rows in the shape of Y. Everybody understands this? The architectural parameter of my neural network. How do I define the number of hidden units, the number of input units, and the number of output units? Are there any questions? Okay. So are we clear about how do we find the size of our input and the size of our output? I'm looking at the chat. So okay. So NH is the number of hidden units. So like I said, we have this design choice. We can have any number of hidden units in our neural network. It's a design choice. You can choose a 10, 15, 20. Generally, my suggestion would be that don't use a very high number of hidden units. Probably go for more deeper networks. So if you have an option of, let's say, having number of hidden units 100, or having two hidden layers with 10 inputs, with 10 hidden units each, I would go for a two-layer network with two hidden layers each with 10 hidden units. Yeah, but it's a design choice. You can choose it. And generally, in most application, it would be a wide variety of hidden units would work. And it requires a bit of like practice of the field. You do some exercises, you solve some problem, and then you realize that, okay, these type of numbers give me the best results. But it's a design choice. So the input output size is fixed. Hidden units, hidden layer, that's your design choice. You can give it any size, any number. Is it clear? What about other people? Are there any questions? If there are questions, please ask them, because this is for your benefit. If you guys are lagging behind, please ask questions. I don't mind answering questions, but try to stay with the class so that you can get benefit from these exercises. So I see a few yeses, but it seems like majority of people have some confusion because I don't see it. So if there's any confusion, please ask questions or just say that I don't get it and I will explain other things. So is it clear to everyone? Okay. Okay. So still not a lot of yeses. I'll just go to the my iPad and just explain it once more because it seems like people do not have clear understanding. So let me just. Okay. So how does this work? What is my setup? So you have to train a neural network. You are given certain input and you are given certain output. This is the data, the training data that you are given. Okay. The two constraints for my neural networks is the number of input of my neural networks have to match the size of my data, input data. And the number of outputs of my neural networks have to match the size of the output of the given data. So for example, in this case, let's say X is 2 times 200. So each data point has two components and you have 200 data points. And Y is 1 times 200. So you have a single vector with 200 elements, one for each data point. And this is either 1 or 0. It's a label of your data. Okay. So now how many input units should my neural network have? 2, right? Because it has to match the data. How many output units should my neural network have? 1, because it has to match the size of my output data. Okay. What happens inside here? The hidden units. What happens with hidden layers and hidden units? That's a design choice. Hidden layers and hidden units. This is a design choice. So for example, in the first example that I'm doing, I choose one hidden layer with 10 units. But you can use any combination of these. It's not fixed. Okay. Is it clear now how I'm like constructing the architecture of my neural network? Can I get some yeses in the chat so that we can move forward and actually implement the exercises? Okay. Okay. Okay, thank you. Please, guys, ask questions. If there are questions, ask them. Don't be shy, because it will give me a better understanding of what to explain and what needs more explanation. So, what are the hidden units? Hidden are okay. Hidden units are the number of components in a hidden layer. So, for example, uh, so I'm going to draw the architecture for my current problem. So, the current problem I have two input units, one output unit. And I have decided that I want to have one hidden layer. So I have a hidden layer here. How many units do I have in this hidden layer? I can have 3, I can have 4, 5, 6, 7, 8, whatever I choose. And then my architecture would be tailored accordingly. For example, in this case, if I choose like 1, 2, 3, 4, 5, 6, 7, then my architecture is like this. Okay, and here is the output. What is the motivation of it? Why do we use it? Well, the goal is that what is the input feature? The input feature is just spatial coordinates, right? It's the x and y coordinate. We hope that as we go deeper in the network, different layers learn more complex features. Okay. For example, we want this one to maybe learn something like be like x square, this one to be like xy, this one to be like, I don't know, sorry, x1, x2, x1 square, x1, x2, this one to maybe x2 square, maybe x1 square, x2, this one maybe it learns like x1, x2 whole square, something like that. So we want these hidden layers to learn the bases, the bright bases which are of importance to us. We don't fix the bases, we want the network to learn. So the number of units would define how many possible things you can learn. The more units you give, the more things you can learn. The more layers you give, the more complex things you can learn. Okay, is it clear? Okay, so it seems like things are a bit clearer now. So let's go to the code. So again, we have defined the number of input units, output units, and hidden units. Next, we initialize our weights. So what would be the, guys, you guys have to help me write the entire code, at least the important things. I would not move because I want you guys to be engaged. So what would be the shape of W1? What should I write? So the number of columns of W1 have to match the number of rows of X or Ni. So what should be the, okay, thank you very much. It's NHNI. So what would be the shape of B1? B1 would be, what would be the shape of this? The number of rows of B have to match the number of columns of W. These are just scalars. So remember that, I'll just write it here. So Z1 is W1 W1 times X plus B. Put a star here. So what would be the size of B1? B1 is a column vector, and it rows have to match the rows of W. Any guesses? It's from simple linear algebra. Anybody wants to take a guess? Exactly. It's NH times 1. NH times 1. Because you can see that you are adding Wx with B, and you can only add it if the number of rows for these two are same. If the number of rows are not same, then we cannot add it. And the number of rows not for X, product of Wi times X. Okay, so the number of row for Z1, and these are NH. Okay. What about W2? So W2, thank you, Aisha. That's exactly correct. So this is NONH. And what about B2? Again, the number of rows of B2 has to match the number of rows of W2. So this is exactly this. It's NO1. Thank you. Now we have to define the helper function. So we have get z. Similar to yesterday, it takes in x, w, and b, and the output is wx plus b. We have to have sigmoid. It takes in z and returns 1 divided by 1 plus bx minus z. Okay, if I'm making a mistake somewhere, please let me know. Then we have to define a loss function. It takes in a y and a y hat, and it returns minus y time b dot log plus epsilon minus 1 minus y times np dot. Why am I adding epsilon in the log? It's not in the definition, but I'm adding it. Guesses? Because we don't want the situation where we have log of 0. Okay, so I've added, exactly, thank you. I've added a small constant here just to avoid this situation. And which axis should I add along? I want to add the loss for each data item. Data items, each data elements are present in different columns. So should I add along rows or along columns? So my data is in columns. The size of y is 1 times 200. So should I add along rows or columns? Which axis should I add along? Guys, you can make any guess. It doesn't have to be like a perfect answer. It's fine. Just if you have a feeling, answer it, and then we can correct it together if there is any mistake. So for the loss function, my x is equal to 1. Thank you. We are adding along columns because the data elements are in columns. Okay, now let's define some parameter for our learning rate. What else do we need? We need to append the loss somewhere. And I think now we can do it for a certain number of iteration. Let's say we give it 1,000 iteration. First, let's write the forward pass. Forward pass is to calculate the output of the neural network. So what would be the first component of the forward pass that we calculate? What is the output of the first layer? The first linear layer. What do we call it in our notation? Remember, the output of linear layers, we call them A, and the output of output of linear layer, we call them Z, and the output of activation layer, we call them A. So what would be the output of the first linear layer? Z1, right? Because it's Z and it's for the first layer. We'll call it Z1, okay? Or you can call it Z superscript 1, but I'm just going to use notation Z1. Okay. And what would be the input of the function get z? What would it take? It takes three things. It takes an xwb. So what should I give it here? The input of the neural network is what? It's x, thank you, and w1 and b1. Okay. How do I define a1, which is the output of the activation layer? It's just sigmoid of z1. So now I have the output of the first layer. How would what would I do to get the output of the second layer? What should be Z2? What would be the output of the input of the second layer? Thank you. This should be A1, W2, and B2. And what would be the output of the activation layer? It would be just sigmoid of Z2. And now that I have the output of my neural network in A2, I need to calculate the loss. So I can say L is equal to get underscore loss, and it takes in Y and A2. Remember, A2 is equivalent to Y hat. Y hat is the output of the neural network, and in my case, I call it A2. Okay, so we are set. Now let's append it to our loss vector. Now we need to do the backward pass, calculate the gradients. So remember, gradient, we start from the end, right? So we would have to calculate the gradient with respect to Z2 first, right? So what was the expression for dZ2? You can even look it up from the slides that you have, but you have to let me write it. Exactly, this is A2 minus Y. Thank you. What is, based on this, what can we calculate? We can calculate dW2. What is dW2? So this is dZ2 matrix product with A1 T. Is it this? Could you just double check it for me? And dB2 should be np.sum. dZ2 x is, again we are summing along columns, x is equal to 1 and keep dims equal to true, because we want it to be stable during broadcasting. Okay, so we keep the dimensions, we don't drop the dimensions in the addition. Okay, now we need to calculate dZ1. What should be dZ1? It should be, from your notes, you can see that it would be W2 times dZ2 element-wise product. Yes, there is a 1 by m before, because it's in their loss, they write 1 by m, all of them. You remember from the very early lectures, I decided to drop this 1 by m in order to not get this issue. Okay, but you can do it. You can write 1 by m. I just generally avoid it because I don't want these positive constants. They do not change much. In any case, you can think, you would see that for dW2, dB2, dW1, and dB1, you have this factor of 1 by n. So it's basically the gradient vector is multiplied by a constant, 1 by n. So I'll just drop that constant. Okay, just to keep things a bit clean. Anyway, so then you have to multiply it with the derivative of the sigmoid function. So this should be 1 minus A1. Okay, and the rest you can just copy it. And make it dW1, dZ1. The input is X here. This is dB1 and dB1. Hopefully this should be fine. Let's just double check it. So dZ2 is A2 minus Y. dW2 is dZ2 matrix product A1 transpose. This is dZ2, X is 1, keep things true. dZ1 is W2 transpose times dZ2 times A1 1 minus A1. It seems fine. Let's just run it and plot the loss. Okay, what's going on here? Oh, I haven't updated the weights, so I have to update the weights. Learning rate time dW1. So W1 is equal to W1 minus learning rate times dV1, and W2 minus equal to learning rate times dW2, and B2 minus equal to learning rate times dV2. So let's run it now. That's actually fairly nice. You can see that the loss function is decreasing, and we are actually learning something. So everyone clear about what we did. How did we calculate the forward pass? How did we calculate the backward pass? Is everyone on the same page? Are there any questions? Okay, I want to see 26 yeses in the chat before we move on. If there are any questions, please ask them. Don't be shy. Okay, so it seems like it's clear to people. I have quite a lot of yeses, which is a good thing. Now let's extend it to, let's say, 3 layers. Okay, so if I have 3 layers, I would have to use number of hidden units in the first hidden layer, and let's say number of hidden units in the second hidden layer. Let's say this is 20. Now you guys have to help me change these matrices. So what would W1 now be? Okay, thank you, Aisha. This is NH1. What about the second component? Sorry. Yeah, second component is fine. It should be the number of input. What about B1? Okay, B1 is also NH1. So some people are writing NH2. So the way I'm saying is that I have an input, then I have the first hidden layer, the second hidden layer, then the output. So that's why I'm using NH1. So my architecture is like this. So it's input. So hidden layer 1, then I have hidden layer 2, and then I have output. So that's why I've used hidden layer 1 first, and I'll use hidden layer 2 and the second layer. So what happens to W2 now? What would W2 do? So W2 is NH2 times NH1. What about B2? This is NH2 times 1. Is it clear to everyone? Because the input of W2 is of the size NH1, and the output of W2 has to be the size NH2. Okay, I want to see some more yeses so that we can move forward. Okay, perfect. And now we would have a third W, because we have increased a layer. So this would be W3, B3. And what would be the size of this? This is NONH2 and NO1. Yes, NH3 times NH2 if you have a third hidden layer, but we don't have a third hidden layer. The output of the third layer is the actual output. So that's why it's N0. Okay. So now this would be the same. We would have what should be Z3 and A3? What should be the input of Z3? Okay, it's A2, W3, and B3. So it's the output of the previous layer, which is A2, weights of the current layer, which is W3 and B3. Okay, and this is just this. Loss would be the loss of this. Now, the first thing that I would need to calculate is DZ3 now. What would happen here? How should I change it? So what would be DZ3 equal to? Yes, it's A3 minus Y. Thank you. Uh, what would DW3 and DB3 become? Again, DW3 and DB3 depends on DV3. So this would become DV3. And what is the input of this layer? It's not A1 now, it's A2. So this would become A2. Okay. Similarly, this would become DW2. This is DG3. What should be here? Instead of W2, what should I put now? Basically, you have to increment everything. You have added a layer, so everywhere there is a quantity for a layer, you have to add it by one. So this would become W3. This would become A2. This would become A2. Then this would become DZ2. The input is A1. This would become DZ2. Is it clear to everyone? Okay. Now let's copy it. And let's call it DZ1. So this would be W2, DZ2, A1, 1 minus A1. So you see that sometimes there is A in the product and sometimes it's X. So think of X as A0. Okay. If you think of X as A0, then everything is same pattern. So the A2, A1, A0. Okay. So everything flows in a regular pattern. Then you have DZ1 here and DZ1 here, and then this becomes W3 and B3, and W3 and B3, and you can extend it to any n layers. It can be 50, 60, 70, 80, I don't know, depending on your application. And this is like everything we did by hand. Let me just double check it that everything is fine. A3 minus Y, DV3, A2 transpose, this seems fine. W3 transpose A2 minus 1 minus A2, that's also fine. This seems fine. This seems fine. This seems fine. It seems like it is indeed fine. Let's run it. And let's see. So it does indeed converge. So now, in today's lecture, what we did is that we can, for any problem, we can create a neural network of arbitrary depth, arbitrary architecture, and calculate its forward pass and backward pass, i.e. train it. Okay, which is actually a very good thing. Neural network is essentially the main component of machine learning. These are called universal function approximator. Given enough complexity, it can approximate any function. So now what I want you guys to do is to use neural networks to solve the problems that we created yesterday. So remember, we had like this different complexity problems. Some of them we could not solve with linear regression, logistic regression, sorry. So now use different sizes and depth of neural networks to solve these, particularly the checkered board pattern. Try it, give the neural network different depths and different neuron numbers, and see if you can actually try to, if you can learn to classify a checkerboard pattern. Okay, I will put this notebook up on the website, but at the end of the lecture, I want you guys to give it a try yourself. You see, it's quite simple. There isn't any extremely complex thing in it. So these equations are directly imported from yesterday. Um, this is exported from yesterday, but just extended to like 3 layers. And then these equations are new, but you have them in the notes. You should be able to implement them quite easily. Okay, so try to solve these questions. Spend some time in the code, try to learn its structure. Um, Extend neural network to maybe 4 layers, 5 layers. This is the last time, by the way, that you would have to explicitly write the expression for calculation of gradients of a neural network or any machine learning algorithm in this class. From tomorrow, we would use PyTorch, but it's good to see what happens at the back end of PyTorch, not just use it as a blind tool, but we know that these equations are exactly what are implemented at PyTorch backend. Now we would just use the high-level API of PyTorch and not write these codes ourselves. Okay, so I'm going to be available on the chat if there are any questions. You have the exercises for today, which is solve the data, try to classify the data that we had yesterday for logistic regression with neural networks. Any questions? Okay, so with this, I will stop sharing my screen and allow you guys some time to actually practice this. Thank you, guys. I'm available in the chat if there are any questions.